In the last section, we talked about sets and subsets, as well as different relationships between sets. In this section, we're going to talk about the cardinality of sets, as well as extend this idea of sets to the idea of a function. So, the cardinality of a set is just another way of describing how many elements are in the set. And so we use this notation here. If A is a set, we say the cardinality of A, which is denoted with A with sort of absolute value bars around it, to mean how many elements are in the set. And we say that a set A is finite if the cardinality of A is equal to n for some natural number n. So as long as there's finitely many elements, right? So some natural number of elements in the set. We say that a set is infinite if it is not finite, and I should probably add here, and non-empty. Right? So every set is either going to be empty, if it's the empty set, or it's going to be finite, or else it's going to be infinite. So, to give you an example, if A is the set consisting of the numbers 1, 2, 3, 4, and 5, then we would say that the cardinality of A is equal to 5. Of course, it has 5 elements. If B is a set consisting of the elements 4, 5, 6, 7, 8, it also has a cardinality of 5, because it has 5 distinct elements in it. But what is the cardinality of A union B? Remember, union is when we sort of join two sets into one larger set. And we have seen in a previous example that A union B would be, well, everything in A and B grouped together. So 1, 2, 3, 4, 5, 6, 7, and 8. So the cardinality of this set is the number of elements in this union. Well, there's 8 elements in this set, so we would say the cardinality is equal to 8. Well, notice that even though we joined these two sets together in a sense, we didn't get that the cardinality of the union was just the cardinality of A plus the cardinality of B, right? It's not just 5 plus 5. That would have been 10. And so when you're trying to find the cardinality of a union of two sets, it's not enough to just add together the cardinality of one set plus the cardinality of another. And this might seem obvious when you're looking at an example like this, but it's an easy thing to forget when you're looking at a problem in context and sort of not thinking too carefully about any potential overlap. Before we move on, it's maybe worth pointing out, we could also find the cardinality of the intersection. Remember, the intersection is the set of elements that are in both sets. So the only elements in both sets are 4 and 5, which means the cardinality of the intersection is going to be equal to 2. There's 2 elements that lie in both sets. Okay, well, if we want to try and find a formula for the cardinality of the union of two sets, we use something called the principle of inclusion-exclusion. So if A and B are finite sets, the principle of inclusion-exclusion tells us the cardinality of the union. And if we want to think about how that works, well, let's say we have 2 finite sets. Here's A, here's B, and maybe they overlap in some particular way. We could try to start by finding the cardinality of the first set A. In other words, find how many elements are in this set here. Then we can try to add to that the cardinality of B. That's how many elements are in this set here. But the problem here is that we've now, maybe we should have used a different color. Let's see. That's not going to work. We've now double counted any elements that lie in the intersection. Right? Any elements that lie in both A and B have been counted twice. They were counted when you looked at the cardinality of A, and they were counted again when you looked at the cardinality of B. We don't want to count them twice. We only want to count them once, which means to compensate for this double counting, we have to subtract the cardinality of A intersect B. And this is what the principle of inclusion-exclusion says. It says to find the cardinality of the union, add together the 2 cardinalities of the individual set, and then subtract the cardinality of the intersection. And we can verify that this works in this last example here, that the cardinality of A union B was equal to the cardinality of A plus the cardinality of B minus the cardinality of the intersection. Right? The union had 8 elements, A had 5, B had 5, and the intersection we said had 2. Okay, so this principle of inclusion-exclusion works in this particular example, but hopefully the Venn diagram demonstrates why it works in general. Now, if you're in a scenario where your 2 sets A and B happen to satisfy that their intersection has cardinality 0. In other words, there are no elements that are in both A and B. Well, essentially what that means is that the principle of inclusion-exclusion in this case would tell us that the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the cardinality of the intersection, which is 0. That's saying the cardinality of A plus union the cardinality of A union B is just equal to the sums of the individual cardinalities. That only happens when the cardinality of the intersection is equal to 0. That is, when the two sets have nothing in common, when the two sets are disjoint. Okay, so that makes sense, right? If A is equal to the set 1, 2, 3, and B is equal to the set 4 and 5, they have nothing in common, and so when you union them together, you get everything in A along with all the new elements of B, so you get that the cardinality of the union is equal to the cardinality of A plus the cardinality of B. But this formula only works when the two sets are disjoint, when they have no elements in common. So let's try to look at an example using this principle in context. Suppose that each of the 25 students in a class is majoring in math or computer science or both. If there's 18 computer science majors and there's 12 math majors, how many students are double majoring in math and computer science? So the first thing that I want to point out is that because they're telling us there's 18 computer science majors and 12 math majors, some of those students are getting counted twice here, right? Because they're not saying there's 18 students who are majoring only in computer science. If that were the case, then this would be accounting for 30 students, and that doesn't make any sense because there's only 25 students in the class. So some of these students, the double majors, are being counted in both of these counts here, right? So what we need to do is we need to frame this as a problem where we have two sets, and we're looking at their union versus their intersection, all right? So let's say C is the set of all computer science majors in the class. Some of these students might also be math majors, right, if they're double majors in both. And similarly, let's let M be the set of math majors in the class. So what we know is that everyone in the class, all 25 of these students, are either a computer science major, a math major, or both. So we know that the union of these two sets is going to give you the entire class. So the cardinality of the union is 25. It's all the students in the class. We also know that there are, there's 18 computer science majors, so the cardinality of C is 18, and the cardinality of M is 12, because there's 12 math majors. Okay, now if we wanted to, we could jump into drawing a Venn diagram of the situation and seeing if we can figure out how many students there are in each of these sections. So here's the computer science majors, here's the math majors. What I know is that this entire circle for C, in total, is going to have 18 people. Oh, I should have done that in blue to be consistent with up above. Okay, and I know that this entire circle for the math majors is going to have 12 students altogether. But I don't know how they're divvied up. In particular, I don't know how many students are in the intersection. That's what I'm trying to find. So the principle of inclusion-exclusion tells us that this cardinality of the union is going to be equal to the cardinality of C plus the cardinality of M minus the cardinality of the intersection. And because I know 3 of these already, this is a simple linear equation to solve. 25 is equal to 18 plus 12 minus this intersection, which is what we're looking for. Let's call that x for now. So 25 is equal to 30 minus x. Okay, so x has to be equal to 5. That means that there's going to be 5 students that are both computer science and math majors because they're in the intersection of the two sets. They satisfy both of those, being a computer science major and a math major. With this in mind, I can fill out the rest of the Venn diagram if I wanted to. I know that there's a total of 18 computer science majors, and 5 of them are already accounted for in the intersection here, which means there's 13 students who are computer science majors but not math majors. Similarly, there's 12 total math majors, 5 are accounted for here, So there are 7 students who are math majors but not computer science majors. Okay, and you can double check that when you add these all together, 13 plus 5 plus 7, you get the total of the 25 students in the class. Okay, so using the principle of inclusion-exclusion allowed us to figure out just how many students fell into each of these categories. Now, we're going to expand on this example here and say, let's look at the previous example, but what if instead there were 4 students in the class who are majoring in neither computer science nor math? All right, so the total number of students in the class is 25. There's 4 students who were non-math, non-CS majors. There's 18 computer science majors, and there's, what did we say? I gotta go back. 12 math majors. This is gonna change things now, right? Because I know that in this Venn diagram, in the end, here's my computer science majors, here's my math majors. There's 4 students that are sort of outside here in the box, right? Here's our entire class. There's 4 students who are neither math nor computer science. And so what we have to account for is the fact that when we add up the number of students who are just CS majors and the number of students who are double majors and the number who are just math, it's not going to add up to 25 anymore. Instead, I wanted to add up to only 21 because I want to make sure that when I add up these 4 sections, it all adds up to 25. So that means there's 21 students that are either CS or math, or both. So I'm going to use the same technique here, I just needed to take this extra step at the beginning. So now I know that the cardinality of the union is going to be 21 students, and it's still going to be the case that this is equal to the cardinality of the computer science majors plus the cardinality of the math majors minus the cardinality of the intersection. So this is going to be 18 plus 12 minus, let's call this y. This is what we're looking for, the intersection. So 21 is equal to 30 minus y. All right, that tells me that y is equal to 9. In other words, there are 9 students that are both computer science and math majors. So I can fill that in now in my Venn diagram. I know that there's 9 students that are double majors. Using the same reasoning as last time, that tells me there's 9 computer science majors that are non-math majors, so that it adds up to 18. And there's 12 math majors altogether, so there would be 3 math majors that were not computer science majors. And one more time, we can add this all up to make sure that all students in the class are accounted for. 9 plus 9 plus 3 plus 4 should give us the total of 25 students in the class, and it does. All right, now this particular problem sort of used an idea that's going to come in really handy and that we already saw in the warm-up for this section, which is using the idea of the cardinality of the complement of a set. Okay, the cardinality of the complement tells us that if A is a set within some finite universe U, then the cardinality of A plus the cardinality of A complement has to be equal to the cardinality of the union. All right, let's remember what A complement is. If A is our set inside some universe U, A complement is everything outside of the set. All right, it's all of this stuff out here. Okay, so it makes sense that when you add together everything in A, right, everything in here, along with everything outside of A, you get everything in the universe. This is really just using the principle of inclusion-exclusion. Using the idea that A and A complement are disjoint. And their union is the entire universe. Oops. And A union, oops. A complement is the entire universe. Okay. So this follows directly from the principle of inclusion-exclusion. But more importantly, this is often how we're going to use it. If we want to find the cardinality of A complement, we can just find the cardinality of the entire universe and then subtract the cardinality of A. We'll see that sometimes it's easier to do that than it is to try to find the cardinality of A complement directly. And we saw that on that cube problem in the warm-up, and we'll see it many times throughout the class. Okay. Now, one last example before we wrap up the section. Does the principle of inclusion and exclusion extend to more than two sets? So if we wanted to find the union of three different sets, can we extend the principle of inclusion and exclusion? And we can. We can extend it even further than that if we wanted to, but it gets very messy, as you will see. So let's say we have three sets, A, B, and C. Maybe they intersect in some particular way. And we want to find the cardinality of the union. How many elements are in either A or B or C or some combination of these? Well, we can start off the same way we did with the cardinality or with the principle of inclusion and exclusion for two sets, which is find the cardinality of A plus the cardinality of B plus the cardinality of C. And just know that we're going to be overcounting here, because if we start with the cardinality of A and then we add in the cardinality of B, already we've double counted everything that looks kind of green in this diagram, right? Everything that's in A intersect B. And now additionally we add in C. Ooh, now we've double counted a whole bunch of stuff, right? We've double counted everything that's in any of the overlapping areas. So we need to account for that by subtracting stuff out again. So what I'm going to do, let's use a different color here. I'm going to subtract this intersection here, because I know this got counted both with the cardinality of A and the cardinality of B. So let's subtract the cardinality of A intersect B. Similarly, I want to subtract the cardinality of A intersect C, because this stuff got counted twice. And I want to subtract the cardinality of B intersect C, because everything there got counted twice. Except what's happened with this middle section here? We originally added it in 3 times, right? However many elements are in all 3 sets, I accounted for them here when I looked at the cardinality of A, and the cardinality of B, and the cardinality of C. But then I subtracted those elements when I subtracted A intersect B. I subtracted them again when I subtracted A intersect C, and I subtracted them again when I subtracted B intersect C. So the stuff that's in the intersection of all 3 sets has now not been accounted for at all. We counted it 3 times and we subtracted it 3 times. And so the last thing we're going to do is we're going to have to add back in the cardinality of A intersect B intersect C. Oops, C. I need to add back in the 3-way intersection so that these guys in the middle do end up getting counted exactly once. And this is a principle of inclusion and exclusion for 3 sets. It's messy, and you can try and extend this to more than 3 sets, but it just gets messier. All right, and so we'll see in the exercises how we can use this for more complicated problems.